Let me share something that still amazes me after all these years of studying the sky. The moon, the most familiar object in the night sky, something every person who has ever drawn breath on this planet has looked up at, managed to hide half of itself from us until 1959. Think about what that means. We had already charted distant galaxies. We had already calculated the expansion of the universe. We had built telescopes the size of city blocks and pointed them at objects billions of light years away. And the whole time, the nearest natural body in space was quietly keeping a secret right in our cosmic backyard. I've spent decades in astronomy, and that fact still stops me cold every time I think about it carefully. What makes it even more remarkable is how thoroughly familiar the visible side had become. Long before telescopes existed, people were mapping what they could see with the naked eye. The dark patches, what we now call the lunar maria or seas, were obvious too. Anyone who bothered to look up. Different cultures gave them different meanings. Some people saw a human face in those dark blotches. Others saw a woman's profile. In East Asian traditions, many people have always seen a rabbit, and I find that one interesting because the rabbit appears in stories going back centuries across multiple unconnected cultures. My granddaughter draws a rabbit on the moon every single time I ask her to sketch it. I genuinely cannot see the rabbit no matter how long I stare, but she has absolutely no patience for my doubts. The point is that people were reading detailed stories into those markings for thousands of years. They named them, they wrote legends about them, and the entire time the other half of that same world was sitting just out of reach, completely untouched by human imagination. Now, before we go any further, let's settle an argument that has been causing confusion since the 1970s, when a certain rock band made a certain album title into common vocabulary. The Dark Side of the Moon. You've heard it. Most people, when they hear that phrase, assume it means the far side is permanently dark. Always. In shadow, never touched by sunlight, a cold, lightless place that the sun has never reached. That assumption is completely wrong, and I want you to understand why before we go another sentence further. The far side receives sunlight just as regularly as the side facing us. They alternate just as our own day and night alternate here on Earth. When we're looking at a new moon, when our side of the moon faces away from the sun, it's the far side that's receiving full, direct daylight. The sun is shining on it right then, as bright as any noontime you've experienced. The English word dark carries more than one meaning. It can mean lightless, yes, but it can also mean unknown, hidden, mysterious, uncharted. That second meaning is the relevant one. The far side was dark to human knowledge. It was a blank space on our map of the solar system. Not in terms of light, but in terms of everything we understood. There's actually a photograph that makes this completely clear, and it's one I've used in lectures for years. It was taken just a day or two after a new moon, when only a thin, bright crescent shows on one edge of the lunar disk. Look at the rest of the moon in that photo. The part that isn't the crescent. It isn't pitch black. It's faintly luminous, softly lit with a ghostly glow. What's providing that light? Earth. Sunlight is striking our planet at that moment, bouncing back off the oceans and clouds and continents, and a portion of that reflected light is traveling outward and falling on the moon's near side. Astronomers call this earthshine. Our world, in those moments, is performing as a lamp, a very dim lamp, but a real one. Meanwhile, on the far side, the sun is shining directly. Both hemispheres are illuminated. They just take turns, like everything else in the solar system. The mystery of the far side was never about light. It was about geometry, the fact that one face was always turned away from our observation point here on Earth. So why does the moon always show us the same face? This is perhaps the most common question I get asked, and the most common wrong answer is, because the moon doesn't rotate. And I genuinely love that answer, because it's precisely backwards from the truth, and correcting it reveals something beautiful about orbital mechanics. Think it through. If the moon didn't rotate at all, if it were truly fixed and motionless on its own axis while orbiting Earth, then as it traveled around us, different faces would gradually come into view, the way a spinning top shows you all its sides. A non-rotating moon would present every part of its surface to Earth over the course of each orbit. The reason we're perpetually locked onto one hemisphere is precisely because the moon does rotate. It just does so at exactly the same rate it orbits us. One complete spin on its own axis, one complete trip around Earth. Both take roughly 27 days. That precise synchrony is what freezes one face permanently in our direction. Picture a waltz, two dancers holding each other close, revolving slowly around a shared center point. As each dancer moves around the partnership's axis, they're also turning individually, and the two motions are perfectly matched. They face each other through the entire dance from the first measure to the last, never turning away, never breaking eye contact. That's the Moon and Earth. This condition has a name, tidal locking, and it didn't happen by accident or design. It was imposed gradually by physics. In the Moon's early history, it rotated at a different rate, spinning freely and independently. But Earth's gravity, acting on the slight irregularities and asymmetries in the Moon's mass distribution, exerted a continuous rotational braking force over hundreds of millions of years. That force kept slowing the Moon's spin, degree by degree, century by century, until eventually the rotation period and the orbital period matched perfectly. At that point, the system settled into a stable equilibrium, and the Moon has maintained that orientation ever since. We're talking about something that was locked in place roughly 3 or 4 billion years ago. Here's something that adds a layer of wonder to all of this. The Moon's gravity is affecting us in return. Our planet isn't immune to its companion's gravitational pull. The Moon raises tides in Earth's oceans, and those tides, through a complex mechanism I won't fully detail here, are gradually transferring angular momentum between the two bodies. The practical effect is measurable. Earth's rotation is slowing down very slightly year by year. Our day is getting longer by about 1.4 milliseconds per century. That sounds trivial, but run it backwards, and you realize that hundreds of millions of years ago, an Earth day was only about 22 hours long. The dinosaurs experienced a slightly shorter day than we do. Even further back, in the earliest chapters of Earth's history, days may have been as short as 6 hours. The Moon has been gently, persistently braking our planet for billions of years, and simultaneously, the energy extracted from Earth's rotation is being fed into the Moon's orbit, causing it to very slowly spiral outward. The Moon is currently moving away from us at about 4 centimeters per year, not a theory, but a measured fact, confirmed by laser-ranging experiments that bounce light beams off reflectors, left on the lunar surface by Apollo missions. Everything in this system is connected in ways that took us centuries to fully appreciate. Before spacecraft existed, astronomers weren't entirely without options for peeking at the hidden hemisphere. Nature provided a small but exploitable loophole. The Moon's orbit around Earth isn't a perfect circle. It's slightly elliptical, meaning the Moon moves a bit faster when it's closer to us and a bit slower when it's farther away. Its rotation rate, however, remains constant throughout. This creates a mismatch. Sometimes the orbital motion gets slightly ahead of the rotation, sometimes it falls slightly behind. The visible result is that the Moon appears to rock gently back and forth from east to west over the course of each month, as though it's slowly shaking its head. There's also a north-south rocky motion caused by the fact that the Moon's orbital plane is tilted relative to Earth's equatorial plane. Astronomers call this phenomenon libration, from the Latin word for balance scales, those old-fashioned two-pan scales that tip and sway as weight is added to one side. By watching these oscillations carefully over weeks and months, 19th century observers could peer around the edges of the visible disk and glimpse narrow strips of terrain near the limb that briefly rotated into view. The total additional area accessible through libration amounts to about 6% of the far side. Dedicated? Astronomers mapped those slivers with great care. But the remaining 94%, the vast central portion of the hidden hemisphere, was genuinely, completely, unreachably unknown, not poorly documented. Not subject to debate, simply absent from human knowledge. The space age ended this situation with a speed that's difficult to fully appreciate from the vantage point of today. On October 4th, 1957, a metal sphere roughly the size of a large beach ball was placed into Earth orbit, and the modern era of space exploration began. What followed unfolded with breathtaking velocity. Just 15 months after Sputnik, barely enough time for a baby to learn to walk, the Soviet Union was already launching probes toward the moon. The first one missed. It flew past the moon without hitting it, continuing out into the solar system, and rather than announce a failure, Soviet officials reframed the outcome with considerable elegance. The spacecraft had achieved the velocity needed to escape Earth's gravity well, sailed past the moon, and entered a permanent orbit around the sun. It was, technically and genuinely, the first artificial planet ever created. Not a satellite of Earth, a satellite of the sun. That satellite is still out there right now, completing its quiet circuits. Someday, someone will find it and put it in a museum. The second Soviet probe, launched later in 1959, actually hit the moon. It impacted in a region that old maps labeled, with memorable unpleasantness, Tuzhostebane, the Bay of Putrefaction. That name has since been replaced by the considerably more dignified Bay of Lunik. The spacecraft hit at roughly 2 kilometers per second and was certainly destroyed on impact. But before launch, the engineers had loaded it with small pentagonal medallions bearing the Soviet coat of arms. Those medallions scattered across the impact site and are still there today, lying on the lunar surface, untouched by anything since the moment they landed. No human or robot has visited that site. When someone eventually does, those badges will represent the oldest human-made objects on the moon, the first material deliberately placed there by people. But the real turning point in the history of lunar exploration came in October 1959 with Luna 3. I want to spend some time on this mission because even now, after everything we've accomplished in space, what those Soviet engineers pulled off seems almost impossible. Their objective was to fly a spacecraft around the back of the moon, photograph the hidden hemisphere, and transmit those photographs back to Earth. That sounds like a reasonable goal, but consider what they had available. There were no digital cameras anywhere on Earth in 1959. Digital imaging technology didn't exist yet. There were no microprocessors, no integrated circuits, nothing resembling modern electronics. The only method of photography known to humanity at that time was chemical film photography. You expose the film in a camera, then you develop it in a tray of liquid developer, fix it in a separate chemical bath, wash it thoroughly in water, dry it carefully, and only then do you have your negatives. A darkroom process that normally requires a human technician, a controlled environment, running water, and at minimum half an hour. The Luna 3 engineers had to miniaturize this entire sequence, automate every step, and make it work flawlessly inside a spacecraft the size of a washing machine in the vacuum of space, with zero possibility of human intervention if anything went wrong. And then there was the film itself. Soviet photographic film in 1959 was not of the quality required for this mission. The engineers needed extremely fine-grained, high-sensitivity film, the best available anywhere in the world. Obtaining it proved to be one of the more remarkable footnotes in the history of space exploration. This was the height of the Cold War. American intelligence agencies were operating a program of high-altitude balloon flights over Soviet territory, carrying photographic equipment designed to capture images of military installations from the stratosphere. Soviet air defenses regularly intercepted and shot down these balloons. When the wreckage was recovered, it contained, among other things, Kodak film of very high quality. The engineers building Luna 3 recognized immediately that this captured American film was far superior to anything they could obtain through official Soviet supply channels. Without making a formal request, without seeking approval, they quietly diverted some of that recovered film for use in their spacecraft. Among themselves, they referred to it simply as film from the American balloons. Their supervisors, apparently, exercised a certain diplomatic incuriosity about where the film had come from. The first photographs ever taken of the moon's far side were made on captured American spy film. I've been telling this story in lectures for years, and it never fails to get a reaction. Luna 3 flew out toward the moon, oriented itself using sensors locked onto the sun and Earth as reference points, opened its camera shutters, and photographed the far side on that captured Kodak stock. Then the miniaturized darkroom went to work. The film was developed in chemicals, fixed, washed, dried, and scanned by a rudimentary optical system that converted the image into a radio signal. That signal was transmitted back to receiving antennas in Crimea. The entire sequence worked. The photographs arrived. They were grainy. They were contaminated with radio noise. Large portions were blurry or poorly exposed. But they existed. The first images human beings had ever received from the moon's hidden hemisphere. When I think about the engineers who made that happen, working with 1950s technology, I feel something very close to awe. Soviet scientists at Moscow State University and colleagues at Pulkovo Observatory devoted weeks to analyzing and cleaning up those images. They were trying to make sense of a blurry, noisy signal that represented something no human eye had ever seen. From what they could distinguish, they began assigning names: the Sea of Moscow, the Sea of Dreams, craters honoring Joliot-Curie and Lomonosov, a geographical feature called the Bay of Astronauts, which is interesting because Gagarin hadn't yet flown when this name was chosen. Astronaut was still the standard term in Soviet scientific writing at the time. These names appeared on the first published maps of the far side, and since this was an era when postage stamps served many of the communicative functions that social media serves today, those maps were reproduced on stamps and distributed to millions of households. People held the first map of the moon's far side between their fingers and felt it without quite realizing what they were holding. And then there was the Soviet mountain range. Examining those early images, astronomers believed they could identify a long, bright ridge running across a section of the far side. A genuine mountain chain. They named it the Soviet mountain range. It appeared on official maps. It was sculpted in raised relief on globe models produced in subsequent years. I personally saw one of those globes, a magnificent meter-wide model at the Cosmonautics Museum in Kaluga, with every geographical feature rendered in 3 dimensions. And the Soviet mountain range was right there, standing up from the surface, prominently labeled. The international astronomical community objected mildly to the political flavor of the name, but Soviet scientists held their ground. They were the discoverers, naming rights were theirs, and the name would stand. It stood for years. It appeared in textbooks. It was incorporated into the received geographical vocabulary of lunar science. There was just one problem. It wasn't a mountain range. It didn't exist. What those blurry early photographs had captured was a bright stripe on the surface. Not elevated terrain at all, but a region of higher optical reflectivity. 2 ancient impact craters, widely separated, had ejected light-colored material during their formation, and that material had fallen in a connected streak across the landscape between them. From a distance, through bad photographs and wishful interpretation, it resembled a ridge. It wasn't. Better images eventually resolved the question completely, and the Soviet mountain range was quietly, unceremoniously erased from the maps. The Sea of Moscow is still there. Lomonosov crater is still there. The mountain range turned out to be a ghost, an artifact of humanity's first uncertain attempt to read a new world from the worst possible data. That, I want to say, is not a failure. That is science functioning exactly as it should. Form hypotheses from available evidence, revise them when better evidence arrives, and get on with it. Now I want to turn to what I consider one of the genuine deep mysteries of our solar system, a mystery that stares at us every time we look at the moon, but that most people never think to ask about. The 2 hemispheres of the moon are profoundly, fundamentally different from each other. Not slightly different, not different in minor details. Different in a way that challenges our basic understanding of how rocky worlds form and evolve. Look at any global map of the moon, and the asymmetry jumps out immediately. The near side, the side humans have watched for all of recorded history, is roughly half covered by vast dark plains. These are the Maria, the so-called seas, named in an era when astronomers genuinely weren't certain whether they might be bodies of liquid water. They're not. They're ancient lava flows, places where enormous meteorite impacts billions of years ago fractured the crust deeply enough for molten rock to well up from below and flood the surface. That basalt cooled to the flat, dark plains we see today. The features visible to the naked eye, the shapes that have been interpreted as faces and rabbits and toads across cultures and centuries. The far side has almost none of this. The great dark Maria essentially disappear when you look at the hidden hemisphere. One modest feature, the Sea of Moscow, qualifies as a sea, along with a handful of smaller patches. Everything else is ancient rugged highlands, heavily cratered, geologically old, compositionally different. The color-enhanced maps generated from orbital data tell this story in vivid terms. The near-side Maria show up in blue-gray tones, the highland regions in yellowish-green. The far side is almost entirely that yellowish-green, wall-to-wall. Those color differences are real and meaningful. They reflect genuine differences in rock composition. The dark Maria are basalt, dense iron-rich volcanic rock. The highlands are anorthosite, a lighter calcium-rich rock that represents the original lunar crust. Human eyes can barely detect these color differences in ordinary observation because the contrast is so subtle, but push the saturation in image processing and the moon becomes surprisingly colorful. Two completely different geological regimes, separated by a line that runs roughly along the boundary between the two hemispheres. The same object, the same world, and yet the two faces look as though they belong to different planets. The Apollo seismographs gave us the first real clue about why this might be. Those instruments placed on the surface by astronauts in the early 1970s allowed scientists to map the moon's internal structure the same way we use earthquake waves to map Earth's interior. What they found was startling. The moon's crust is not uniformly thick. The near-side crust is measurably, significantly thinner than the far-side crust. This thickness difference matters enormously for what happened to each hemisphere. Thinner crust offers less resistance to the magma pressing upward from the hot interior. When a large meteorite punches a deep crater into thin crusted terrain, it's much easier for lava to breach the fractured rock and flood the depression. That's how the Maria formed: impact, fracture, lava flood, cooling. On the far side, with its thicker crust, the same impacts occurred, but the crust held. The magma couldn't punch through. The basins remained dry. The asymmetry in crustal thickness produced the asymmetry in surface appearance, but that just moves the question back one level. Why is the near-side crust thinner? This is where the most compelling current hypothesis enters, and it involves Earth itself and the moon's violent infancy. The moon, when young, orbited much closer to our planet than it does today. We know this because, as I mentioned earlier, the moon is measurably moving away from Earth at about 4 centimeters per year right now. Run that number backwards over billions of years, and the young moon was dramatically closer. Early Earth, meanwhile, was dramatically hotter. Still in its formative period, still radiating enormous amounts of heat from its molten interior and from the ongoing energy of accretion. A young, hot Earth sitting close to a young moon would have heated the moon's near side significantly more than the far side. The near side faced the heat source, the far side faced cold space. That temperature gradient, maintained over millions of years in the moon's early history, meant the two hemispheres cooled at different rates. The far side solidified first, building up a thicker, more rigid crust. The near side remained partially molten longer, producing a thinner, weaker crust, one that was far more vulnerable when the great meteorite impacts came. This is an elegant hypothesis, and most planetary scientists find it persuasive, because it explains multiple observations at once: the crustal thickness difference, the distribution of the Maria, the overall geological asymmetry of the moon. Earth shaped its companion in the most fundamental way possible, right from the beginning. For most of the 20th century, physically reaching the far side with a spacecraft was considered extremely challenging, not primarily for reasons of navigation or propulsion, but for a much more prosaic reason: radio communication. Any spacecraft operating on the near side of the moon has a permanent, unobstructed line of communication with Earth. Signal goes up, signal goes down, mission controllers stay informed, but the far side presents an impenetrable barrier. No radio signal can travel through thousands of kilometers of solid rock. A lander or rover operating there would be completely, permanently cut off, unable to send data, unable to receive. Commands deaf and mute relative to Earth. The Chinese space program solved this problem through methodical preparation. In May 2018, they launched a relay satellite called Kuekiao, meaning Magpie Bridge, a name from Chinese mythology, into a special gravitational equilibrium point located about 65,000 kilometers beyond the Moon, called the second Lagrange point of the Earth-Moon system. From this location, the satellite has a permanent line of sight to both the far side surface and Earth simultaneously, a relay station floating in space, bridging the communication gap. With the Kuiqiao relay in position, China's Chang'e 4 spacecraft became the first in history to achieve a controlled landing on the far side of the Moon, touching down in January 2019 inside the von Karman crater, which lies within the enormous South Pole Aitken Basin. That basin deserves a moment of attention. It is one of the largest confirmed impact structures in the entire solar system, roughly 2,500 kilometers in diameter and about 8 kilometers deep at its lowest point. And it's ancient enough that billions of subsequent smaller impacts have churned and mixed its surface material into something more homogeneous than a freshly formed crater would show. You can see it clearly in topographic maps as a vast depression dominating the Moon's southern far side hemisphere. Despite its enormous scale, it never flooded with lava the way the great near-side basins did. The far side crust, even here, was apparently too thick to allow magma to breach it. The biggest impact in the region was still not enough to trigger the volcanism that created the near-side seas. Chang'e 4 carried a small rover named Yutu-2, Jade Rabbit 2, which rolled out onto the surface and operated for 6 full years until 2025. 6 years on terrain that had never been touched before by any human instrument. The sample return mission followed in 2024. A Chinese spacecraft landed in the South Pole Aitken Basin, deployed a robotic arm and a small drill, collected material from the surface and subsurface, sealed it into a return capsule, and launched it back into lunar orbit. There it rendezvoused with a transfer vehicle that carried the samples the rest of the way to Earth. A tiny rover that accompanied this mission, nicknamed the Golden Toad by the mission team for the gold foil thermal insulation covering its exterior, photographed the lander from the surface nearby. Gold foil is standard practice in spacecraft design. It reflects infrared radiation and helps manage the extreme temperature swings in the lunar environment, and it happens to produce a striking visual effect that journalists found irresistible. When the sample capsule reached Earth, scientists from institutions around the world were given access to the material. What they found in those samples, mixed in among the expected lunar minerals, was something that required a moment to fully absorb. Particles of terrestrial origin, fragments of Earth deposited on the Moon by ancient meteorite impacts, so powerful that they lofted debris from our planet's surface into trajectories that eventually intersected the Moon. We've long known that meteorites from the Moon reach Earth. They're a recognized category of extraterrestrial rock, identifiable by their distinctive chemistry, but the reverse traffic had never been confirmed until those samples were analyzed. The two worlds have been exchanging material throughout their histories. In the distant past, when large impacts were far more frequent, this exchange was probably considerably more active. We are, in some small but real chemical sense, made of the same stuff. The far side of the Moon spent the entirety of human history as a blank, not an uncertain sketch, not a rough outline based on incomplete data, but a complete and total absence. No information whatsoever. In 1959 we saw it for the first time, and the images were barely distinguishable from noise. 60 years later we landed on it. A few years after that we brought pieces of it home. What we found in those pieces, the faint fingerprints of Earth's own rock, mixed into lunar soil after billions of years of meteorite exchange, is the kind of discovery that reframes how you think about the relationship between worlds that share a neighborhood in space. And what we are planning to build there, the radio observatories that will use its silence to listen to the universe at frequencies never before accessible to human instruments, may turn out to represent one of the most consequential pieces of scientific infrastructure ever placed beyond Earth's surface. The far side was the last great blank on our nearest cosmic map. It isn't blank anymore, but the most interesting chapters are still being written, and I expect to find the next few decades of this story very interesting indeed.